Welcome to this video on exploiting symmetry in high-dimensional dynamic programming. This is joint work with Magdi Kahu and Jesse Perla at University of British Columbia and with Arnab Sot at Carnegie Mellon University. I am Jesus Fernandez-Villaverde at the University of Pennsylvania. The motivation for our paper is that most models in macroeconomics and other related fields deal with two classes of environments. The first class of environments is representative agent models, either in the canonical real business cycle or New Keynesian models. Sometimes there is a small variation of this model where we have two agents. For instance, in models of financial frictions where we have a borrower and a lender, and in models of international business cycles where we have home and abroad. The second type of models are environments with a continuum of agents, like in the canonical Kurzweil and Smith model. However, there are many models of interest that deal with a finite but large number of agents and aggregate uncertainty. Think about models with many locations, countries, regions, metropolitan areas, industries. These models have become very popular during the last year because they have been used to study the spread of COVID-19 and the local interactions. Models with many households, such as overlapping generations or different types ex ante, instead of a continuum of households as in Kurzweil-Smith. Models of industry dynamics with many firms. Models of networks. These models have become increasingly popular as we accumulate more and more microdata, and thus we have more and more empirical observations that we want to match. The challenge is that in most models with a finite number of agents and aggregate shocks, agents need to keep track of their own states and the states of everyone else, so that they can forecast future prices and thus make optimal decisions. To illustrate this, think about an n locations business cycle model in the tradition of the classical work by Backus, Kehoe, and Kidland, 1992. In this model, an agent in location n needs to know her own 8 state variables, but also the 8 states in each of the other n-1 locations in the economy. That means that if we are working with a version of the model with 50 locations, which will be a business cycle model of the 50 different states of the union, you will end up with 400 state variables. And how do you solve a model with 400 state variables? Well, a possibility will be to follow what Backus, Kehoe, and Kidland do. And they have two countries, so they need to solve for 16 variables, which is to use a variation of a perturbation a la Judd and Gu, for instance, on first-order approximation. You can also use some type of linear quadratic approximations, which under certain circumstances are equivalent. But we often deal with problems that are inherently nonlinear. Think about models with occasionally binding constraints or non-ergodic. For instance, when we are dealing with models with many locations, sometimes it's hard to think about the existence of a steady state because one location or one firm may be growing faster than other locations. Or we may be dealing with large transitional dynamics. We know that perturbation approaches do not work very well when we have either strong nonlinearities or non-ergodic behavior. What about sparse grids? Well, the problem is that even the most aggressive approaches a la Broom and Scheidegger 2017 cannot really be pushed beyond 30 state variables or so in most real-life applications. Of course, that doesn't imply that sparse grids are not very useful. It means that we can deal with models with 20 or 25 state variables, but it also means we are not going to be able to deal with models with 400 state variables. What about something that looks like Kurzweil and Smith, where instead of keeping track of all the states, we just keep track of some moments of them? Wait for it, because this is going to resurface later in this presentation. At the core of why handling a model with 400 state variables is difficult is, of course, the course of dimensionality. If you go back to the original book by Richard Bellman in 1958 on dynamic programming, you will see that he discusses the course of dimensionality in page 9. And he points out that this course of dimensionality has two aspects to it. First, that the cardinality of the state space is enormous. This has complications just in terms of computing the solution, but also even more pragmatically in storing the solution, because you will need homogeneous memory requirements. Think about a model with 266 state variables. And in that model, you have a grid of 2 points per state, low and high. You cannot go any lower than 2 points per state. Or currently, if instead of solving using, let's say, value function iteration, you are using a tensor of 2 polynomials per state. For instance, a level and a slope, and again, you cannot go much lower than that. Well, this model with 266 state variables will have more elements in the grid or more coefficients in the tensor of polynomials than the Eddington number, the estimated number of protons 10 to the power of 80 in the universe. And we are not talking here about a gigantic model. Think about, as I was mentioning before, a model of the industry, and you have 2 or 3 firms, 2 or 3 state values variables per firm. As soon as you have 80, 90 firms, you are already in 266. Or in our example before of a multi-region model of the US business cycle, you have 400 state variables. There is a second aspect of the course of dimensionality, which Bellman already mentions, but that economists sometimes do not appreciate enough, which is that it's very difficult to evaluate highly dimensional conditional expectations. Because you have a lot of state variables, you will need to evaluate things like continuation value functions or Euler equations that involve integrals of future values of those state variables. And computing integrals is an exponentially hard function of their dimensions. Solving an integral in 10 dimensions is much harder than solving an integral in 2 dimensions. And that puts a bound on how accurate of a solution we can get. So what do? We are going to try to address this challenge by introducing the notion of permutation invariant dynamic programming and the associated concept of permutation invariant economies. These concepts are built around the idea of symmetry, which is an old tradition in economics that goes back decades. We mentioned over there 2 classic contributions by Samuelson in 1990 and Mertens and Judd in 2018. However, in the interest of keeping this video relatively short, let me skip the literature review. The common feature of most models, perhaps of interest, is that the policy functions of the agents are the same. They are just evaluated at different points. That's our idea of symmetry today. Let me give you a very concrete example. Let's go back to our multi-location model of the US. What symmetry means is that in a lot of these models, if the representative agent in California had the same capital and productivity as Texas, it will behave as Texas and vice versa. The differences between Texas and California are not that they have 2 different policy functions, it's that the policy functions are evaluated at different points. That means that when we are solving the model, we don't really need to care if the state with high productivity is California or the state with high productivity is Texas. We need to care about how many states have high productivity. In fact, there are even many forms of ex-ante heterogeneity, like differences in discount factor that can be motivated by differences in demographics between Texas and California, that can be encompassed as pseudo-states. I will come back to that later on. In this particular example of the discount factor, the pseudo-state will just be the discount factor. The solution of the model, as I was mentioning before, will be invariant under all the permutations of other agent states, because the equilibrium often is about removing labels or indexes. Think about what the Walrasian auctioneer does in competitive equilibrium. The Walrasian auctioneer takes the excess demand from agent 1 and sums it to the excess demand of agent 2, and so on and so forth, and then quotes a price that clears the market. But the Walrasian auctioneer couldn't care less whether the agent with a lot of excess demand is agent 10 or agent 27. It only cares about the total excess demand. And that's the insight that we are going to exploit. More in concrete, how does permutation invariance help? Because it tackles the two components of the course of dimensionality pointed out by Bellman. First, the value and the policy functions of the dynamic programming problem belong to a very particular family, the family of permutation invariant functions. In particular, they can be represented exactly using a latent dimension. And this latent dimension can be possibly much lower than the number of states. That means we are not going to be dealing with the 400 state variable dimension problem, but with the latent dimension, which perhaps, let's say, is 22. That's a much easier problem. And this will actually help us to understand why the Kruskal-Smith method works as n goes to infinity. Because what the Kruskal and Smith method does is really reduce the problem of keeping the whole distribution into the latent variable of the states of that distribution. Second, we are going to have a fast concentration of measure. You can think about concentration of measure as a fancy law of large numbers for equilibrium objects such as value and policy functions. In particular, we are going to have things like the expected value function or the expected policy function, and what we'll have over there is that to compute those conditional expectations, instead of having to resort to a Monte Carlo with a lot of draws or to a very complex quadrature, we will only need to draw once from the distribution of idiosyncratic shocks. And because of concentration of measure, the value function evaluated at that one single draw of the distribution and the expected value function will be close enough for numerical work. Interestingly, this is a situation where in general you do not want to set the shocks to zero, which will be the intuition of perhaps many researchers in economics. And the reason is because to evaluate an integral, an expectation, properly, what you want to do is to draw from the typical set of a distribution. The typical set is defined in information theory as the set that accumulates most of the mass of the distribution that you require to evaluate accurately the expectation. It turns out to be the case that the typical set of distributions as standard as the normal distribution is not the mode, but an orbit around the mode. And that in fact, as you have more and more dimensions, that orbit moves away from the mode. So if instead of drawing from the distribution, what you are going to do is setting the shocks to zero, you are actually going to get a very inaccurate evaluation of the value function. And then, once we have taken care of the individual shocks, we can always evaluate the aggregate shocks using a quadrature. That means that in practice it's going to be perfectly possible to handle models with thousands of state variables. And our application today will have as many as 10,000 states. And it will be perfectly feasible if you give me enough memory to handle millions of states. And we are going to do this in a regular laptop, and we are going to be able to get solutions that I will argue are going to be extremely accurate in just a couple of minutes. And we are going to do that by using a deep learning approach. In particular, we will train a neural network that is going to implement the permutation invariant dynamic programming problem as dictated by your representation theorem. Instead of just throwing this problem to a neural network and hoping the neural network somehow will come up with the right solution, we are going to design the neural network architecture to take advantage of the fact that we know that the solution is permutation invariant. Strictly speaking, dealing with neural networks is not required, because the only thing that you really need is a flexible functional basis that will implement the approximation theorem, for instance through a projection. Nonetheless, neural networks have some numerical advantages. We know that neural networks are universal nonlinear approximations, which means they can approximate a very large class of nonlinear functions, and moreover that they scale very well. Second, we have great libraries such as PyTorch Lightning, which are state-of-the-art and well tested by the industry. That means that the researcher, instead of starting from scratch in every paper, can rely on a lot of software, and the code will be quite simple, transparent, and easy to debug. And finally, because the neural networks are going to be massively parallel, and in particular, we can implement our architectures on graphic processing units like the ones that 99% of laptops and desktops have nowadays. So how do we pick our application to show that all of this works? And every time you write a computational paper, there are two routes. Route 1 is I can introduce a sophisticated application where our method quote-unquote shines. By delivering results it will be difficult to show in other circumstances. Or I can show you how our ideas work in a well-known example. In this video, I do not really have the time to tell you about the methods and the application and yet keep the video in under a reasonable length. And besides, if I were going to tell you about a sophisticated application, how do you know that our solution works, that the solution is actually accurate? So what I'm going to do is I'm going to present a very well-known example with a twist. We will do something slightly different. And leave for another day the more sophisticated applications. So our application is going to be a variation of Lucas and Prescott 1971 model of investment under uncertainty for N firms. Why? 4 reasons. First, because if you go to Luchmis and Sargent 2018, perhaps the most popular textbook in graduate macro, in their pages 226 to 228, the authors use this model by Lucas and Prescott to introduce recursive competitive equilibria. In that sense, we are going to deal with the model that is the simplest possible model of recursive competitive equilibria and yet easy enough that it can be used as an educational tool. In fact, the model is so simple that it will fit on one slide. But this is a very rich model because with one parameterization, I'm just going to pick one parameter. I'm going to make it equal to 1, and then the model is going to have a known linear quadratic solution, which will give me an exact benchmark against I can compare my neural network approximation. And in that way, I will show you that our solution will be extremely accurate, and moreover, that the classical control solution, which in general will be of order big O and 3, will be costly to compute when n is very, very large, where our solution is going to be of big order O1, and that's of order big O1, and that's why I was asserting before I will be able to compute, given enough memory, models with millions of state variables. But by just changing that parameter I mentioned before that was equal to 1 to something different, like 1.5, the model will be nonlinear. In fact, I can make it really nonlinear, and yet our method is going to handle the nonlinear case as easily as the LQ case. I will only need to change one number in one line in my Python code. And according to the Euler residuals, because in this case we are not going to have a known solution, the solution is still going to be of high accuracy. Without further ado then, let me get into the core of the paper. What we are going to do is going to introduce a big X, little x dynamic programming problem. This is the most standard dynamic programming problem in economics that I can think of. So there is absolutely nothing in this slide except notation. Consider the problem of an individual agent that has an individual state little x. To make notation easy, I'm going to assume that this is a scalar, but it could be a vector. V is going to be the value function, and the value function is going to also depend on a vector big X that stacks all the individual states of all the agents in the economy. And that value function of little x big X is going to be equal to the max on the control U of a return function that depends on the individual and aggregate states and the control, and a discounted expected continuation value function where beta is the discount factor. There is going to be a law of motion for the state of the individual that depends on a function little g, which is a function both of the choice and of the state. Think, for instance, about a budget constraint that says that my assets tomorrow are equal to my assets today plus my income minus my consumption. Consumption in this case will be the control. And it's going to be subject to some individual shocks, for instance, a shock to my income, and aggregate shocks, for instance, a shock to the real interest rate. And then there is going to be an equivalent law of motion for big X, although now we take out U because from the perspective of the agent, the behavior of all the other agents in the economy is given. And this is a moment where I need to emphasize that we are going to consider cases or environments where the agent is a price taker and it does not incorporate into her decisions the fact that she's affecting the aggregates in the economy, either because she is too small to matter too much, or because for whatever the reason we think this is a sensible approximation. I come back later to say a few things about non-atomic agents. I need to introduce a couple of mathematical concepts, not very deep, but they will be useful in a second. In particular, let me tell you about a permutation matrix, which is nothing more than a square matrix that has a single one in each row and column and zeros everywhere else. These matrices are called permutation because when they pre-multiply a conformable matrix A, they permute the rows. And if I push multiply, what I'm permuting are the columns. So let's think about Sn as the set of all n factorial permutation matrices of size n times n. For example, S2 will have two components, and it will be the identity matrix and the matrix 0, 1, 1, 0 that switch the two rows of any conformable matrix A. If you know a little bit about this, Sn happens to be the symmetric group under matrix multiplication. And we are going to take advantage of the algebraic properties of the symmetric group to do a lot of the heavy lifting in the proofs of our theorems. But you don't need to worry about it because they are not going to be, these algebraic properties are not going to be important to follow this video. So now what I can do is I can introduce the idea of permutation invariant dynamic programming. So a big X, little x dynamic programming problem is a permutation invariant dynamic programming problem if for all state variables and all permutations pi that belong to the symmetric group, the reward function is permutation invariant. That is, if I just switch the agents in the big vector X and the return is the same, if the deterministic component of the law of motion is permutation invariant, that is, I again rotate the elements of the vector x in G, and nothing happens, I will just take G of x and rotate it. And then, if I have the covariance matrix of the idiosyncratic shock satisfying that pre-multiplying and post-multiplying it by the permutation matrix does not have any effect. Okay? So if these three conditions are satisfied, then my dynamic programming problem is a permutation invariant dynamic programming problem. And there is a quite a straightforward proposition that follows from it. If the dynamic programming is permutation invariant, then it's also the case that the control, that is the policy function, and the value function are permutation invariant functions, where I can take x, do any permutation, and I will have still the same control, and I'll take x, do any permutation, I will have the same value function. Coming back to my example before, what this is saying is that if you're California, you don't care if the state with high productivity is Wisconsin or Minnesota. And if you switch the states of Wisconsin and Minnesota, you as California, as the representative agent in California, are still going to have exactly the same decision rule and exactly the same value function. Okay, why is this useful? Why is it useful to know that your control and your value function are permutation invariant? Because then you are going to be able to apply main result 1 in our paper, which is about the first aspect of the course of dimensionality, which is the representation of permutation invariant functions. This proposition, based on Wagstaff et al. 2019, although there are other papers in the literature that make similar points, says, let's take a function f of Rn plus 1 into n, because, remember, we have n agents, each of them with one state variable, and then we have the additional individual variable of agent 1. Be a continuous permutation invariant function under the symmetric group. That is, we take f, we permute x in any way, big X in any way possible given the pi's, we still have the same f. Then there exists a latent dimension L less or equal than n, the big dimensionality of the problem, and continuous functions rho from L plus 1 into R and phi from R into RL, such that f of x, little x, big X, is equal to rho of little x and then this mean over here that goes over the components of x. So let's think about what phi does. So phi is saying, look, let me go over the states of all the agents in the economy and compute a function of L aspects of it. The first thing you can think about here, and that's in fact what we are going to use later as part of our implementation, the first L moments. Okay? So phi goes from 1, let's say from R1 into R4. That is the first moment, the second moment, the third moment, and the fourth moment. And then we combine it in rho between the individual state and these 4 moments that will give us exactly f. This theorem is more powerful than it seems and is less powerful than it seems. Let me start with the later. Why is less powerful than it seems? Because the dimension, the latent dimension, L, can be exactly equal to n, which doesn't really make much of a progress. Okay, the proposition is not trivial because it's if and only if it goes in both directions, but you may need to care about situations like the Leontief production function, where since you are caring about the mean, you want to know in all situations all the elements of your vector of inputs into the production function. Of course, I will argue that in this situation, you really don't want to use this representation theorem. You want to use some other representation theorem that takes advantage of the fact that the Leontief production function only cares about the mean. But it's more powerful than it seems, because L, we have learned in many situations, can be much, much lower than n. And in fact, in the application I will show you later on, we can show that L is equal to 1 even if n is 10,000. But because you don't really need in real life to get the equality. Let's suppose, for instance, that L, the real L, is 20. It may be the case that with L equal to 10, the representation is close enough to f for all practical purposes. And you have moved then from dealing with a problem of, let's say, 10,000 state variables to one that in the exact latent variable is 40 but is good enough with 5. And solving a problem in the 5 dimensions is much easier. This proposition should remind you of Crusoe-Smith, because that's exactly what Crusoe-Smith do. They say, look, you have the whole distribution, in their case it's a continuum, and we take the first moment, or perhaps the first 2 moments, and that's not going to be the exact representation, rho, but it's going to be close enough. So you can think about this representation theorem as a generalization of Crusoe and Smith. It's not that we are doing anything against Crusoe and Smith, the other way around. What we are saying is Crusoe and Smith were really very insightful, and they realize you are going to have one component, which is the mean, phi, and then you are going to have another function, rho, which is to be in their basic paper a log function with coefficients that depends on the states, and that's going to deliver what you need. Okay, so in that sense, this is really a generalization of Crusoe and Smith, and that's what I was saying, that when we implement this through the neural network, we are going to be building on the tradition of Crusoe and Smith. How does this theorem work? Well, I'm going to give you an intuition that goes not from R n plus 1 domain, but from 2n, because this intuition will be much easier. So think about a function f that goes from 2n to r. This is basically a function that takes strings of zeros and ones and gives you some value. So a string, for instance, if n is equal to 4, will be 1, 0, 0, 0, and another string will be 0, 1, 1, 0, and another string will be 0, 0, 1, 0. And this function f takes each of these strings and gives you an output. This domain is gigantic. Take n to be 266, as I was mentioning before, more elements in the domain than protons in the universe. But let's suppose that you take a situation where f is permutation invariant. That basically means that you only care about how many ones there are in the string, but not where they are in particular, because you can always rotate them, you can always switch their position in the string. Well, if this is the case, then the function has at most n plus 1 outputs, because you can have 0 ones, or you can have 1 ones, or 2 ones, or 3 ones, etc., up to n ones. Then phi is just the identity function. This is a case where L is equal to 1, and rho maps the sums of ones in the string into the n plus 1 outputs. We have done a gigantic dimensionality reduction. And the point that I want to highlight is that using results from the symmetric group, you can generalize this idea to the R n plus 1 domain and deal with much more general functions. Okay, so the main result one says you have a very high dimensionality and you need to compute the value function or the decision rules. Well, if the environment is symmetric, it has this permutation invariance, you don't really need to solve it in n plus 1 states, you only need to solve them in L. And L may be L plus 1, and L may be much smaller than n. The second main result is the concentration of measure. And what concentration of measure tells us is that under certain conditions, which is basically that the expected gradient of a function is bounded, that function, the expectation of that function is well approximated by the function evaluated at one draw from the distribution of the variables that get into that function. A lot of ideas here, so let me unpack them. Imagine that we have a vector z of random variables that comes from a normal distribution, and that we have a function that maps those random variables into some outcome. So in our environment before, this is the value function that depends on the idiosyncratic shocks of all the agents in the economy. The idiosyncratic shocks come from a normal distribution, and then f is the value function that depends on these idiosyncratic shocks. What we can show is that if that function f is not too wild, then the probability that the function f evaluated at one draw from z minus is very different from the expectation of that function, the probability that these two objects are very, very different, that is bigger or equal than an epsilon for any epsilon, is bounded by that term over here. Okay, so let me repeat that. You're saying I have a function f, like my value function, and I know what the expected value function is. And then I just evaluate f in one draw from the distribution of the z's, and I ask, how likely is that f evaluated at this point and the expectation of f are very different from each other? Well, that probability is bounded by this term. And in this term you will see over here an n in the denominator. That basically tells you that as n becomes larger and larger, this number is going to become smaller. And of course you will need to evaluate this in every particular case, and I will show you some evidence of that in our application. But in practice, when n is maybe 50 or 60, that means that you don't need to worry too much about the randomness of f of z, and that any draw of f of z is going to be a good approximation of the expectation of f or c. Turns out to be the case that with concentration of measure, dimensionality is not a curse, it is a blessing. And as Ledoux put it in 2001, a random variable that depends in ellipsis way on many independent variables, but not too much in any of them, is essentially constant. And that's the whole point about a value function that depends on a lot of idiosyncratic shocks. For all practical purposes, is a constant. And we are writing this in terms of just one draw from the distribution, but I could have maybe 5 draws from the distribution. That will mean that this will be a tighter bound, and I will be able to evaluate expectation of f just by evaluating the mean of f over the 5 draws, and it will still not be very costly. I will not need to do a Monte Carlo with thousands of draws. Okay, so this is, in some sense, by taking just one draw from the distribution, we are going to take the most extreme possible approach. So what have I done so far? I have told you, main result 1, don't worry about having n state variables. What you need to worry is about L, the latent variable. And it may well be the case that L is much, much lower than n. Second point, don't worry too much about the expectation, because you can evaluate them with a single Monte Carlo draw, thanks to concentration of measure. Let's see how all of this works in real life. And what I can do is I can introduce the permutation invariant economy that I hinted at a few slides back. We can have an industry consisting of n larger than 1 firms, each producing the same good. A firm I produces output X with X units of capital, just making production equal to capital to eliminate irrelevant constants. I could also introduce decreasing returns to scale to production, and I will come back to that later. Thus, the vector big X is just the vector with the production or capital of the whole industry. We need an inverse demand function for the industry, where with some mu bigger or equal than 1, and this is our twist, this is the only difference with respect to the model in pages 226 to 228 of Lurch, Smith and Sargent, is equal to a constant 1. I could have over here an alpha, but this makes things easier. 1 over n, the sum of the production. If nu is equal to 1, then this is just the mean. The model in that case is going to be solvable using the linear quadratic optimal regulator. When nu is larger than 1, the distribution of x's will matter, and then we will need to solve the model using some type of nonlinear approach. In the spirit of price taking that I mentioned before, the firm does not consider the impact of its individual decisions on P of x. Due to adjustment frictions, investing U has a cost gamma divided by 2 U to the square. And we are going to have a law of motion for capital, where the capital tomorrow, which is also the production tomorrow, is 1 minus depreciation, the capital today, what we invest, an idiosyncratic shock, and an aggregate shock. So a very standard law of motion for capital. And the firm is going to pick the sequence of investments to maximize is expected discounted revenue, where the discount factor is beta and the revenue is just, or the net revenue is just the total amount of sales, the price given by the inverse demand function times x, its own production, minus the adjustment cost. Okay, so as promised, the model completely fits in one slide. I can write the model in a recursive formulation. This is absolutely nothing in this slide except just to introduce the value function that depends on the return today plus the continuation return tomorrow, and then of course the loss of motion for capital today with respect to capital tomorrow for the individual agent and for everyone else in the economy, given that you take these decision rules as given. And thus we can introduce our concept of a recursive permutation invariant competitive equilibrium, which is exactly the same definition that of a standard recursive competitive equilibrium, except that we are going to impose that the optimal policies are symmetric. So in that sense, we are going to have a value function, we are going to have a control, an optimal control U, and loss of motion for the capital, such that given the optimal policy functions, the value function is the value function that solves the recursive problem from the previous slide for each agent, and U is the optimal policy function. The optimal policy function is symmetric, that is, we switch agents, we permute agents, and it will be the same, and the laws of motion for capital satisfy the law of motion, just their definition from before. Okay, so this is a very natural and transparent, I believe, extension of recursive competitive equilibrium to the situation where you are doing permutation invariance. The Euler equation for the firm will just equate the rate of return of investment tomorrow with the cost today. The cost today is given by the adjustment cost, is this left-hand side over here, and the return tomorrow will be what we get in extra production and what you get in changing the amount of capital tomorrow after depreciation. This Euler equation will be helpful later when we actually solve the model. That's the only reason I'm presenting it over here. Okay, so we want to find a global solution for the model, and we are going to set a high bar for ourselves because we don't want to get a solution that is accurate around a point like the steady state. That's what you get when you are doing things like perturbation. We want to have solutions that are global in the sense that they capture well the behavior of the economy very far away from one particular point. Why? Because we may want to compute large transitional dynamics, because we want to compute the effects of large shocks, etc. And we are going to find our solution using the representation of permutation invariant functions that we introduced before. And that basically means that we know that u of little x big X is this function rho of little x, the capital of each firm, and this function phi of the capital of all the other firms in the economy. The problem, of course, is that in general we don't know rho and we don't know phi. Phi, in addition to it, also means not knowing phi also means that we don't know L, the latent variable. But this is precisely the type of situations where deep learning helps, because deep learning does a great job in approximating functions rho and phi that we don't know. We are thus going to specify different deep learning architectures, h of theta, where theta are going to be the coefficients of the architecture, that is how different inputs and outputs are related, inspired by our previous representation theorem, but where we don't know phi or rho. In particular, we are going to approximate phi in two different ways. One will be as functions of a finite set of moments of the distribution, inspired, of course, in Krusell and Smith, but phi will be, but we are going to allow that to do it in a fully nonlinear way, as in Fernandez-Villaverde, Nuño, and Hurtado in our paper on the financial frictions and the wealth distribution. And we are going to use either one moment or 4 moments, and I will tell you later why we pick both. Or we can say, look, maybe the moments of the distribution are not the best ones, the best way to capture some important features of the distribution. So let me approximate the distribution using a flexible rectified linear unit network, which is one of the standard default neural architectures that people use these days all the time, with 2 layers each with 128 nodes. That means that we are going to have a very highly parameterized neural network with between 50,000 to 67,000 coefficients. In addition to it, Rho, the outer layer of the approximation, will be a highly parameterized neural network with 4 layers. Some of you may be concerned that we are dealing with a very highly parameterized approximation. But turns out to be the case that a surprising benefit of these highly dimensional approximations is the double descent phenomenon in machine learning, as documented recently by many papers like Belkin et al. And Advani et al. Surprisingly enough, having more coefficients in the neural architecture makes it easier for the architecture to find minimum norm solutions, not harder. All the code for our approach, for our implementation, is done in PyTorch Lightning and is run on GPUs. Again, as I was saying before, to be sure that this is as easy as possible for the researcher and in terms of the GPUs to take advantage of massive parallelization. Let me give you a little bit of intuition about how this moments architecture works, about how the ReLU architecture works, so we can move right away to the training of the network. So remember, we are going to have an outer layer, the Rho, that takes X and something that comes from the phys, that will be over here. And then what we have is the different X's, we compute moments from 2 to M, and that will give us the approximation that we need. And then we have the Rho, and that gives us a solution. Or we can do it in terms of the ReLUs, and the difference over here is that then we are not going to compute moments, we are going to compute these functions phi from 1 to L of the elements in the vector X. And then again we have the outer layer, and that gives us a U. So how do we train the network? Very easy. First, we have an object that we want to minimize. In this case, it's going to be the Euler residuals, which is just the left-hand side of the Euler equation I introduced before, minus the right-hand side. You don't need to do this with the Euler residuals. For instance, you can also do it with the value function. In the Bellman operator, the difference between the value function in the left-hand side and the max in the right-hand side. Or you can do it with many other objects, like a conditional expectation. Happens to be the case that for us, doing it with the Euler residuals is very simple and very efficient. Then we pick a bunch of trajectories for the state variables in our model. Okay? And the only way you do that is you can pick them randomly, for instance, and then just say, well, given some random decision rule and some random initial point, that is going to give us a whole law of motion, a whole path for this. And what we want to do is we are going to evaluate the Euler residuals in some or all the points in these trajectories. And what we are going to do is say, let me pick the coefficients of the network architecture to minimize the square of the sum of the residuals over these trajectories and all these different points. Couple of points about a couple of ideas about this minimization. This is, as I was mentioning before, a very highly dimensional minimization problem, but thankfully we have very good algorithms to solve it. In particular, we have, for our case, Adam, which is just an stochastic gradient descent with adaptive moment estimation. And the very good thing about doing a gradient descent in this environment is that because of the architecture of the neural network, we can compute all the required derivatives very efficiently using backpropagation, which is just a fancy way to say the chain rule of calculus. In fact, I will show you in just 1 second how you can train these neural networks in just a couple of minutes on a regular laptop. We need parameter values. Since I pick a lot of normalizing constants already in the model, there are very few of those. I will have beta, which is 0.95, and I will have gamma, which is 90. And then with respect to the standard deviations of the idiosyncratic and aggregate shocks, I will make the idiosyncratic risk to be 5 times larger than the aggregate risk. And the only reason I'm doing that is because this is the standard case in the real world, that idiosyncratic risk is much higher than aggregate risk. I could do it the other way around, nothing of importance will change. And we will deal with two cases in the inverse demand function. When nu is equal to 1, that will give us the linear demand function, and when nu is larger than 1, that will give us the nonlinear demand function. So why do we do case 1? Because when we have the linear demand function, given that the objective function of the firms is quadratic, what you have is a linear quadratic dynamic programming problem, where only the mean of the xi matters. And that means that we can find the solution of the linear regulator in a second, and that will give us the exact decision rule. Okay? Now, that exact solution is the benchmark against we can compare our deep learning solution. The idea here is, of course, if I'm dealing with a basic Lucas-Prescott model, I will never use deep learning. I already have the LQ solution. But what I want to do is precisely to take advantage of that to have an exact solution in one particular case. Okay? So I take the LQ solution, on my left hand, that's the exact solution. And now I have on my right hand my neural network. And what my neural network is going to do is going to learn, quote unquote, very quickly that the solution has that linear quadratic structure that gives us a linear function of the decision rule on the sum of all the productions, of all the capitals in the economy. And then I can look at the left-hand side, at what my left hand has produced, which is the exact solution, what my right hand has produced, which is my neural network solution. I compare both of them and I say, hey, these are very, very similar. I'm going to do that in a second. But before doing that, I also want to tell you how I check that concentration of measure, that is the role of n, allowing me to get rid of having to compute these very complicated expectations by just doing one draw from the Monte Carlo, is going to work. And for that, what I'm going to do is I'm going to compute a modified linear regulator solution with one Monte Carlo draw instead of setting the individual shocks to 0. For the linear quadratic is one of the cases where, in general, where it's okay to set the individual shocks to 0. Remember, I told you in general that's not the case, but for this particular case it is okay to do so. And in that way I can look at the exact linear quadratic by setting the shocks to 0, the idiosyncratic shocks to 0, and the linear quadratic with this one random draw. And that's a little bit of a bonus point of the model of the paper, because we show you how to implement this modified linear regulator solution, which can be helpful for solving non-Gaussian LQ problems where certainty equivalence doesn't hold. So how do I convince you that this concentration of measure works? Basically, what I'm going to look at the standard deviation of the decision rule tomorrow of the firm with respect, when I'm doing this Monte Carlo draw, with respect to the exact solution that I get from the exact LQ solution. And you can see over here how when I go from having two firms to having 10,000 firms, remember this is where I'm going to have 10,000 state variables, the standard deviation goes down very, very quickly, and by the time I'm already 10 or even when I'm 100, I'm doing sufficiently well. That concentration of measure is giving me everything that I need. Okay? So the way you want to understand figure 1 is saying concentration of measure is very powerful. By the time you have 50 firms, this is good enough with one draw. If you have less than 50 firms, then maybe you need to do 3 or 4 draws. But it's still going to be the case that solving for the integrals is much easier than it will seem without appealing to concentration of measure. But let's go now and compare the exact linear quadratic solution with our deep learning neural network solution. And we are going to do this for 128 firms and for 3 different architectures. When I have the first moment, which I'm going to call phi identity, when I have 4 moments, and when I have the ReLU for the phis. And I'm going to do this for 256 trajectories, and I'm going to give you both the mean square error and the in shaded blue area, the 2.5 and 97.5 percentiles of the errors. And what you are going to see is first in the left panel what happens when the phi is the identity. This is the best possible case for the neural network. Why? Because we know the exact solution only uses the mean. So this is a neural network that has the advantage of knowing a lot about the structure of the solution, and then it delivers mean square errors of order of 10 to minus 9, which is for all practical purposes the exact solution. Okay? But, and this is the really interesting thing, imagine that I never took the class with Lundqvist and Sargent. I never read the book of Lundqvist and Sargent. And I say, I don't know if it's 1 moment, 2 moments, 3 moments, just let me put 4 and see what happens. Well, it turns out to be the case that you are still doing it very, very well. Okay? These errors of 10 to the power of minus 7 is the same that you will get if you were solving the model with value function iteration and tons of points on the grid, or with value function, or with Chebyshev polynomials and a lot of Chebyshev polynomials, except that, of course, with 128 firms, you will never be able to compute it. Okay? So this is telling you, hey, even if you don't know much about which moments to select, this is going to be good enough. And also, when you actually go to ReLU. And this is the one that really, really surprises me, because this is telling me, hey, what if you don't trust that moments can be good enough? For instance, in models with overlapping generations, taking moments of the assets of the agents in the economy may be misleading. You say, let me just throw a ReLU into this overlapping generation model. And you are going to do, at least in the case of this Lucas and Prescott investment decision problem, you are going to do fantastically well. Okay? And to me, this is really very impressive. It's basically saying you don't know much about the problem, do a ReLU on the distribution, do a row on the outer part of the approximation, and you get a solution that is, for all practical purposes, as good as the exact solution. Now, you may be asking, oh, but should I use 10 ReLUs versus 9 ReLUs, 2 layers versus 3 layers? All those fine-tuning parameters are sometimes known as hyperparameters. And my answer is that you will just check different combinations in the same way that when you are using value function iteration, you will check what happens when you have 100 grid points versus when you have 200 grid points. The advantage of doing it with a neural network is that you are going to have PyTorch, which is going to allow you to play with all these hyperparameters in a very efficient way. And the code is going to run very, very fast. Let me show you that these Euler residuals for the ReLU are good enough for all practical purposes. And the way I do it is the following. I initialize the economy far away from the ergodic state. That is, from the area, the region where the economy is spending a lot of time. And basically what I do is I give firms much less capital than what they would like to have on average, so they are going to accumulate capital relatively fast. And given some initial conditions, I compute this transition of the economy for the analytic LQ solution for identity, moments, and the ReLU. And what you can see is that even 60 periods later, all 4 solutions are exactly on top of each other. I actually need to do this a little bit of a zoom so you can see a little bit of the difference between the two. So it's not just that the Euler residuals as shown in this graph are very small, it's that the practical consequences for objects of interest that we care about as the properties, the aggregate properties of the economy, is that we are getting exactly the same result that if we were having the exact solution. And the computation time, here what I'm going to do is show you the median value of training the network 21 times for different numbers of firms, and you will see that the computation time is around 90 seconds on average, maybe 92. Now, you will say why it goes up and down a little bit. Well, this is just because this is a network, this is a random algorithm, so sometimes it takes a little bit more, sometimes a little bit less, and also it depends a little bit on the state of the computer when I jump the simulation. But the important thing is that you very, very clearly can see that this is an approximation, a solution method that has a computational cost of order big O1. As if I go from having 10 firms to having 1,000 firms, it doesn't become more complicated in terms of time. Okay? So the way you want to think about this is just, let me summarize, is I throw this to the computer, I throw my neural network approximation, I get a solution that is as good as the one that I will get if I knew the exact solution, it has the same economic implications, so I'm not missing anything in the economy of importance, and it's very efficient in terms of time. And now, armed with these results, I can go and compute the case where nu is larger than 1. And this is the situation where, as before, I have a non-linear demand function, which means that the whole distribution of x's matter. And this is a solution where the linear quadratic approximation does not work any longer. The great thing about our neural network is I don't need to do anything. I just go to my Python code, I open it, and where nu says 1, I put 1.5. So I need to add 2 extra characters, dot and 5. And that's it. I click, run, in 90 seconds I have the solution. Solution that I will not be able to get with any other solution method that I'm aware, because if I were using a sparse grid, they will crash down for 10,000. If I were going to do a perturbation, I don't think they are going to do so great when we are so far away from their codic state. But I can still check the Euler residuals. Now, the one with only 1 moment is not going to do so well, so let me do the one with 4 moments and the one with ReLUs. We are still having fantastically good Euler residuals of 10 to the minus 6, which the way to interpret them is that in fact we are still having a very, very good solution. But something you could ask yourself is, well, you are claiming this economy is highly nonlinear. How do you know? Well, something I can do is I can plot the path of the economy when mu is equal to 1.0 all the way to 1.5, and you see that they change quite a bit. This, of course, I don't have the exact solution, but I know the Euler equation residuals along this path are very, very small, and that shows you that this economy is very highly nonlinear. This is just not a parallel change of each other. So nonlinearities matter, and yet our solution method does a great job at capturing them. There's of course many extensions that we discuss in the paper in some detail. We can have decreasing returns to scale, where the policy becomes a function of x. That's another different way to deal with nonlinearities. We can have multiple productivity types. We can have complex idiosyncratic states. We can have global solutions with transitions and aggregate shocks, and we can deal with non-atomic agents. In particular, something you can do is say, let's use our neural network to approximate for the atomic agents given the behavior of the non-atomic agent, and then you solve for the interaction between the economy and the non-atomic agent using a standard method. And that simplifies dramatically with respect to the standard way to do it. And that's very nice about our method. Our method doesn't need to be the solution of the whole model. It can be a solution of a block of the model that you can then plug in into the rest of your solution approach. And we are thinking at this moment about how to extend this to network architectures, where who do you trade with actually does matter, and then permutations are not completely invariant unless you redefine the state space properly. So let me conclude. What I hope to have accomplished in this video is to convince you that by taking advantage of the idea of permutation invariant, now we can compute a much larger class of models that we could compute in the past. We can deal with models with rich ex-ante heterogeneity and aggregate shocks, like models with overlapping generations or many different household types. We can deal with models with firm dynamics. We can deal with models of open economy with many locations, or closed economy business cycle models with multi-sectors. And hopefully we will also be able to deal with network models very soon, and with search and matching models. I hope you have enjoyed this video presentation, and I encourage you to read the paper for more details. Thank you very much for your attention.